Number 15, still trying to find intervals of concavity, up or down, and points of inflection. So we need our second derivative, which means we first need our first derivative. And unfortunately, there's no getting around the product rule here, guys. First factor, x, times the derivative of the second, same base to the same power times the derivative of that exponent, which is -3, so I'll cram that out in front. Plus, second factor, e to the -3x, times the derivative of the first, which is just 1. So that's y prime. I do suppose I could, now I wouldn't write this down yet if I were you guys, pull out an e to the -3x, and that would leave us with -3x from this term, and then a +1, which I could rewrite as 1 minus 3x. That would look just a little bit nicer. As to whether or not I should do that, it's really a question of which form of this derivative will be easier to differentiate again, this version right here or this version right here. It looks like both of them are going to require the product rule one time, so I think as fun as what I just did was, you guys, and as proud of myself as I am, I think I should have left this one alone. All right, so let's get to it then. Y double prime of x equals, all right, and one thing at a time right here, we need to take the derivative of this term in red, and that derivative requires the product rule. First factor, ooh, I see it already. Okay, first factor is -3x. I'm not going to write that yet. -3x times the derivative of the second factor, which is same base to the same power times the derivative of that exponent. So what I had in that blank was a -3x, but that now needs to get multiplied by this -3. That becomes a positive 9x. So that was first factor times derivative of the second, plus the second factor, e to the -3x, times the derivative of the first, which is just a -3. And now I don't like that plus minus that I have right there, so I'm just going to make that a big fat minus. And I'm going to close that red bracket, and what we have there is the derivative of the first term of the first derivative. But we still have this guy at the end. So we've got to take the derivative of e to the -3x, which is going to be the same base, e, to the same power, -3x, times the derivative of that exponent, which is -3. And I saw that. That's why I didn't put a plus here. It becomes a -3. But of course, if you had plus -3, that's perfectly fine as well. Ugh. So that's my second derivative, and now I do think it would probably be worth it to take a look at the fact that we have 1, 2, 3 terms in this second derivative, and we can factor actually 2 factors out of it. Oh, now wait a minute. Hang on, Fontana. Those ones can be combined right there. That becomes a -6 e to the -3x. I didn't notice that. So that takes care of all of that. So now there's really only 2 terms, but we could pull out a 3 and an e to the -3x. And that would leave us with, let's take a look here. From the 9, we still have a 3. We didn't touch that x, so that stays there, but we did divide out the e to the -3x. And then at the end of all this, we have a -2. And that's all that's left there. Now, I think that factored version of the second derivative is going to be easier to deal with moving forward. Okay, couple of questions now. Is this second derivative ever going to equal 0? Answer to that is yes. Not from this factor, you guys. E to a power will never equal 0, but from this factor right here, that would equal 0 if x were equal to a positive 2/3. Now, the other thing you should definitely be thinking about is that second derivative ever going to be undefined? And the answer to that is no. An exponential function has an unlimited domain, all real numbers. Same thing with 3x minus 2, and anytime you multiply a real number times another real number, you're always going to get another real number. So that x equals 2/3 is the only, let me say this right, potential point of inflection that we have found so far. Okay, so what are we going to do with that, guys? We are going to make ourselves a sign chart right here. We're going to choose two test values, and we're going to put them into the second derivative. And I really wanted that factored form of the second derivative here, guys, because I thought it would work out a lot nicer. Now, going along with this, let's see, we just spoke a second ago about the domain of this function, which, yeah, looks like it's going to be all real numbers. I want to choose some x values now that are going to be easy to evaluate right here, and I kind of feel like 0 would be a real good one to pick. And then over here on the right, something bigger than 2/3. I think if I chose x equals 1, that'll do something nice for me. So what are we doing? We're going to the second derivative with these, y double prime of 0. Okay, e to the 0 power is going to equal 1, so this whole first factor is a 1, and then this factor right here, 3 times 0 minus 2, is a negative 2. So we have, what did I just say? A 3 times a negative 2 is going to get us negative 6. All I really care about is that it's negative, and it looks like our graph is concave downward on this interval. Then when we jump over here to x equals 1, let's try y double prime of 1. E to the, it doesn't really matter, e to any power is always positive. So this times this, we're going to end up with a positive value there. And then 3 times 1 minus 2 would be positive as well. Positive times positive is positive, so we are now concave up. So putting it all together here, guys, we've got a graph right here that is concave down on, I've been doing interval notation on the last two, but when you really just have two big intervals, I'm noticing the solutions manual has just been saying concave down for x is less than 2/3. And that's the same thing, guys, as saying an interval from negative infinity to 2/3. Either one of those is just fine. We are concave up for all x values greater than that 2/3 right there. Got it? And sure enough, we have a change in concavity. Our second derivative changes sign right here. So we have our lone point of inflection at the spot here where x is equal to 2/3, and those are the answers to what they were looking for here in problem number, wait for it, I forgot, 15. There we go.